Well, thank you so much, Kostya, for the lovely introduction. And as Kostya said, one of the things I want to share with you today is some of the research that we've been doing on birds, particularly members of the corvid family. That's members of the crows. That includes the jays, the magpies, the rooks, and the ravens, as well as normal crows. And there are two photographs up here of relevance to this. One is the scrub jay on your left, and in the middle, the Eurasian jay. And then I've also been doing some work on other species, and one of them that I'll highlight today are these coleoid mollusks, the cephalopods, the cuttlefish, pictured here, octopus, and squid. And the big picture question going to be asking is episodic-like memory like episodic memory? In other words, is the kind of research that we can do looking at the behavioral criteria for experiential memory, our experiences of what happened to us, where and when, like the human episodic memory, which is defined phenomenologically in terms of aspects of consciousness. And to do so, using the same animals, the scrub jays, Eurasian jays, and coleoid mollusks, particularly the cuttlefish, I'm going to be asking questions about memory and mental time travel. But to do so, I'm also going to be using a little bit of magic to look at it, if you like, from the opposite ends of the lens, rather than saying, can they do what humans can do, or can they do hallmarks of what we think are important in human memory, even in the absence of language, or at least in the absence of the ability to test these things based on reading and writing. Can we look through the other lens using magic to look at constraints on cognition? So, what exactly do we mean by mental time travel? Well, it's the ability to travel in the mind's eye, backwards and forwards in time, to think about the past and plan for the future. And in humans, it's often defined with respect to phenomenological consciousness. So we talk about a subjective feeling of re-experiencing a specific personal past, about what happened, where and when. And I'm highlighting in red the conscious phenomenology and in bold the key aspects. So this is something about the self, an awareness that the event happened in the past. So that's something about time. And then the conjunction or the projection of self in time, a realization that these are one's own memories, that we're the author of these memories, and that as a consequence of being the author of them, we create them, we write them in the mind's eye, and we read them as we remember the past. They become our own. And in artistic writings, there's a wonderful little saying, comes from a book of Catherine's, that says, you don't remember what happened. What you remember becomes what happened. So you don't remember what happened because so much is going on. You're selective. And because you're selective and subjective, you remember what's important to you. You don't remember everything that happened. But because we take ownership for these things that happened, and the fact that they happened, not they are happening or they might happen in the future, means this awareness of time past, that we take ownership for them. So you don't remember what happened. What you remember becomes what happened. It becomes the memory of what you think happened. And that's where the magic comes in, which I'll talk about towards the end of my presentation, because that's exactly what magic capitalizes on this idea that you don't actually remember all the objective details of what happened, but because you have a subjective and selective memory, of what you think happened that is based on an awareness of your time in the past and your projection of self in time. You take ownership for this memory that isn't quite accurate, and that's what the magician can violate, because magic requires the magician to violate your expectations, and that's what leads to surprise. So that's why I'll bring magic in at the end. So, of course, the issue with a phenomenological discussion about subjective feelings of re-experiencing things that happen to me and an awareness of when these things happen to me and a realization that this is about what happened to me in the past. And it's all about how I remember what happened to me. In other words, this projection of self in time. If we define it this way, we really restrict ourselves only to investigations in humans, because in the absence of any agreed non-linguistic markers of these aspects of consciousness about self and time and projection of self in time, we can't assess these abilities in animals. So how can we progress forwards? Well, one way is to look at aspects of this that we think we could do behaviourally. And Tony Dickinson and I came up with the idea that you could look at the what, where, when of experiences. And we did this based on this Larson cartoon, illustrates it rather nicely when Gary Larson says all forest animals to this very day remember exactly where they were and what they were doing when they heard that Bambi's mother had been shot. And if Dr. Dolittle were fact, not fiction, and that little snake at the bottom of the picture could really say, I was under a rock getting ready to shed, then I, for one, would be happy to say that despite these inabilities to prove anything about phenomenological consciousness and self and time, we could look behaviourally. So that led us to the idea that we could look at whether animals are able to remember what happened to them, where and when, based on a single trial unique experience. So in the first experiment that Kostya mentioned in his introduction, we capitalised on the fact that these jays hide food for a living. We call it caching based on the French word cacher, to hide. And the idea is that all the birds are hand raised so that we know their exact experiences because we took them from before their eyes opened and therefore could document exactly what kinds of experiences they had. And we gave the degrade group the opportunity to learn that worms, their favourite food, are fresh after a short delay. And they're degraded. They've gone black and are unpleasant to eat after a long delay. And the birds are allowed to cache peanuts as well as worms. And of course, peanuts never perish. So the idea is that the bird should rapidly learn that after a short delay, they should recover their favourite food, the worms, because the worms are still fresh. But after the long delay, they should avoid the degraded worms that have gone bad and instead go for peanuts. And you might think, these two retention intervals are a bit weird. Why did you choose 4 hours versus 124 hours? Well, 124 hours is exactly 4 hours, but 5 days later. So it's to control for any possibility that they're using a circadian rhythm, a biological clock, because this is the same time of day. It's just either 4 hours later on the same day or 4 hours later, 5 days later. But to control for any possibility that memory just degrades over time, we had our different group, our control group, the replenish group, for whom worms are always fresh. So the worms are replaced by degraded worms. So for them, the time delay shouldn't matter, whether it's a short delay of 4 hours or a long delay of 124 hours, then worms are always fresh. And therefore, they should continually search for worms, irrespective of how long ago they cached the worms and the peanuts. So that's the kind of rationale behind the experiment. So it depends on having hand-raised birds, because you want to make sure that everybody is naive. Nobody knows about perishability rates beforehand. And then you want to give one group the opportunity to learn that worms go bad over time. And the other group doesn't get the opportunity to learn that worms go bad because worms are always fresh. And then you look at what they do when they're given the opportunity to cache the worms and the peanuts. And you see that with the 4-hour delay, both groups cache more worms than peanuts, because worms are their preferred food. And they stop caching less over time, because I guess they're less motivated because they just had worms a few days ago. But they continue to preferentially cache worms over peanuts. But at the 124-hour delay, the one where they get the food back 5 days and 4 hours later, you can see that over time, over these 4 training trials, very few training trials, because the birds don't need to be trained to cache, it's something they do spontaneously, that the degrade group are continuing to recover their peanuts that they've cached, but over time they stop recovering the worms, whereas the replenish group continue to show a preference for recovering worms. Now, of course, this is just training. This is just to show that over time they're learning what they should recover based on what they cached. But if you want to test for memory, as I'm sure you've heard in previous lectures from the other professors that have spoken to you over the last 3 days, you'll know that you can't rely on the food being present, because there are other cues that emanate directly from the food. It could be that they could smell the caches and therefore simply go back to where they can smell worms or peanuts. Or it could be that when worms degrade, for example, they ooze something out and the colour of the sand changes. So in test trials, when you're looking at memory, you want to make sure that the food isn't present and that the sand has been replaced by fresh sand. So there are no cues about the food that could directly emanate from the sand. In other words, they can't be smelling or seeing or hearing or touching or anything else. They have to use memory. So in the test trials, the food is removed before cache recovery and the trays are replaced by fresh sand. So we give them a brand new trial. Everything's the same as usual. At the caching stage, they get worms and peanuts to hide. But when it comes to recovery, none of the caches are there. They've all been removed by the experimenter. Fresh sand has been put in the trays have been cleaned, so now they have to rely solely on the memory of where they'd hidden the caches previously, either 4 hours earlier on the same day or 4 hours earlier 5 days previously, in other words, a delay of 124 hours. And here you see the results. So for the replenish group, they go preferentially for the worms, irrespective of the delay, because of course they prefer worms. So they remember where they've cached the worms and they search specifically in those places where they'd cached the worms. There are no worms present because it's a test trial for memory and therefore the food's been removed. Whereas the degrade group switch their searching pattern. After the short delay, like the replenish group, they mainly search for worms. After the long delay, they search preferentially for peanuts and avoid the worms. I've put DW to indicate that by this point, their expectation is that the worms would have degraded. I say expectation because it's a test trial. For memory, there's no food present when they search for the food. Now, skeptics would say, that's great. It shows something about memory. But how do you know that the animals really remembered the experience? Or had they just had a semantic memory about knowing it? And here you see beautiful artwork by the late Ruth Tolving, Endel Tolving's wife. And there, Endel Tolving is talking to his pet cat, Cashew. And there I am talking to one of my scrub jays, Sweetie Pie, doing the equivalent. A worm in your tray, you say, but do you remember it or do you just know it? Is there a simpler memory mechanism based on recognition rather than active recall? Could you just have a memory of something like of relative familiarity? If the trays are really recent in my memory, I go for worms. If they feel much more fuzzy in my memory, I'm aware that I saw them quite a long time ago, I just go for peanuts. I don't have to actually remember. I just have to have a recognition. If I saw it before, I go for worms. If my memory of when I saw it before is vague, go for peanuts. I often call it the conference phenomenon. When you've been at a big conference and you've met many people, you may forget the names of those lovely people you met, but you know they're vaguely familiar. So by this rule, if it's vaguely familiar, but I can't remember, I might go for peanuts. If I have a crystal clear memory, I might go for worms. So to control for this, we capitalized on the fact that these caching trays have, if you like, two sides to them. You could see it as having a top and a bottom, or a left and a right. And so what you can do is cover one side of the caching tray, let the birds cache in one side, then move the blockade that stopped them caching on that side and switch it to the other side and test their memory for that. So this is what it looked like. So you block one side, as illustrated by the black, and you let them cache worms in one side and peanuts in the other. And you can control for the order in which they do it and the side in which they do it. So, for example, you can have them cache worms first on the right or peanuts first on the right. And then you give them a delay of 120 hours. Now, this is a novel test, so there's no food present, so they're neither rewarded nor punished for this experience. They simply cache worms, and then after 120 hours, they're given the opportunity to cache peanuts, and then 4 hours later, they're given their trays back. So in the top condition, that means that the worms are 124 hours old, because there was 120 hours, then the next caching episode, and then 4 hours. Or in the bottom example, the peanuts are 124 hours old and the worms are only 4 hours old. So this is interesting because you make different predictions about the two groups. The degrade group, who have learned that worms go bad over time, should search preferentially for peanuts in the first condition because the worms are old. And they should search for worms in the second condition because they prefer worms over peanuts if the worms are fresh. So when worms are only 4 hours old, they should search for worms. When worms are 124 hours old and have perished, they should search for peanuts. Whereas the replenished group, of course, they just love worms, and for them, worms never degrade. So they should search for worms in both conditions. And that control is important because, of course, a simpler explanation would be that if you found that prediction, that the birds in the degrade group search for peanuts after the 4 hours and worms after 4 hours, you could say they don't need to remember how old the worms are. They simply need to go back to the last item they cached. Peanuts in the top condition, worms in the bottom condition. But if that explanation is true, go for what I cached last, then the replenish group should also show a preference for worms in the top condition and worms in the bottom condition. But they don't. You see that the replenish group consistently search for worms, whereas the degrade group search for worms after the delay in which the worms were recently cached, So the worms are still fresh, but they preferentially switch to searching for peanuts in the trial in which the worms would have degraded. The worms would have been 124 hours old. Would have, not are, because of course the worms are not present. So the birds are searching based on an expectation that's based on the memory of what's happened in the past about how long worms degrade. So remember that phrase, it's based on an expectation of the memory of what they thought happened, because I'll come back to that when we talk about magic and this whole idea of violating expectations of what you thought you remembered. So based on these experiments that we published in Nature in 1998, we argued that these jays have an episodic-like memory based on what happened, where and when. And we called it episodic-like, not episodic, because we have no evidence of the associated phenomenology of their ability to have an awareness of self, of time, and of projection of self and time. But absence of evidence is not the same as evidence of absence. It's simply untestable. And therefore, we argued that could you look at other behavioural criteria that might also fit this idea that these what, where, when memories are consistent with episodic-like memory in humans. So how might you do that? Well, before going on to that, let me show you a brief summary of all the animals that have since been tested. And importantly, in many animals, not to do with me, so in completely different groups, sometimes on the same animals and sometimes on different animals. And by and large, the findings have been highly replicable. So cuttlefish pass, scrub jays pass, pigeons fail, voles and other rodents and rats and mice pass. Rhesus monkeys don't pass. Children pass sometimes, but not always. Depends on age. For children, if they're under the age of 4, they fail. If they're 4 and above, they pass. And then, of course, the great non-human great apes pass. And below, on the bottom of the slide, are some of the authors that have led these pieces of research. So this idea of what, where, when memories has been fairly well documented within the animal kingdom. Not all animals pass, but many do. And now let's look at this idea of whether episodic-like memory is like episodic memory by evaluating other kinds of behavioural tests of episodic-like memory. So to address this question, is episodic-like memory like episodic memory? I've pointed out that there are 3 behavioural components. There's not just this ability to remember what, where and when memory, which is what I've told you about already, but there's also other aspects of the behaviour. So one is the idea of incidental encoding, the idea that when we form an episodic memory, an experiential memory of what happened, where and when, there's a lot of bits of the memory that we didn't set out to remember. We didn't go in thinking, I must remember X, Y, and Z about an event. They just happen automatically. In fact, Richard Morris referred to them as automatic encoding of unattenuated experiences. In other words, just that there are these things that you just happen to remember. They weren't necessarily relevant to the scene. You might later remember something about the fact that because I'm a dancer, my hands move a lot when I'm talking. It's completely irrelevant to this lecture. Or that I must be right-handed because when I use a hand to support my head, I'm using my right arm. They're not things that are relevant to the lecture, but you just happen to remember them. That's incidental encoding. And you can test this by asking whether the animals, including humans, because humans, after all, Homo sapiens, are another species of animal, just one that can read and write, whether we can answer unexpected questions just things that we just happened to incidentally remember. And there's a third thing we can ask behaviourally, which is about source memory. If it's an experiential memory, if it's an episodic memory, then we should remember how we know it. How do I know that London is the capital of London? How do I know about Moscow? Well, I don't really remember how I know those things. I just know them. So they must be semantic memories. Whereas if I can remember the experience of memory, then it's an episodic memory. So I remember, for example, the first time I came to Moscow and had the privilege of watching the Bolshoi perform, because I'm a ballet dancer and huge ballet fan. That is an experiential memory. That's not a fact. The fact is that the Bolshoi performs in Moscow. The memory is remembering the beautiful version of Swan Lake that I saw and all the memories associated with that amazing experiential episode. So the source memory comes in then because we can ask, in humans, we can ask, did I read it or did I hear it? Or you can ask, how did I know it? Because I read it or heard it, or I don't know how I know it, I just know it. But in animals, you can also ask something similar. Because you can ask, did I see it or did I smell it? Did I see it or did I hear it? Using the appropriate sensory expertise of the animals in question. So in terms of other tests of episodic-like memory in animals, if I look first at incidental encoding, here's one example of the jays where we showed them that food was located under cups, and then they had to remember which foods were hidden under which cups how long ago. So that's the what, where, when memories. But the cups had different features on them. Some were patterned, some were coloured. And yes, sure enough, the jays were able to answer those unexpected questions about what was on the cups. And with source memory, we were able to show that indeed the cuttlefish, who can also pass what were when memories of past events based on whether shrimp are available, their favourite food. So that shrimp are like waxworms for cuttles, or the more boring food, crab, which are more like peanuts for cuttlefish. What was on the menu when? And if they know that their favourite food, shrimp, will be will be available for dinner, they eat less crab at lunchtime. And here you can see one of our cuttles just moving across the scene. Well, when I talked about mental time travel at the beginning, I pointed out that it was not only about the past, it was also about the future. So what about the evidence then that they can anticipate and plan for a future need prior to behavioural execution? Well, we know that the cuttlefish, as I mentioned a minute ago, eat fewer crab at lunchtime when they know that shrimp are available for dinner. But is there any evidence of future planning, of without any training, the ability to spontaneously use memories of past experiences to plan for the future? Well, let me share with you one example.
But is this just another example of instinctive behaviour to survive the winter? Or is there something far more complex going on? It's a question that's greatly intrigued Professor Nikki CLAYTON. She studies western scrub jays, another American corvid, renowned for its caching behaviour. Nikki wanted to discover whether they could do more than just remember where they'd buried food in the past.
If they can travel back in their mind's eye to think about the past, can they also travel forward in the mind's eye to think about the future? Can they imagine the future, if you like? Can they plan ahead?
To find out, Nikki created an experiment based on a very human annoyance: waking up to find that breakfast is off the menu. For 6 days, the birds were housed in this aviary, split into 3 zones. In the middle is the dining room, where the birds were fed during the day, and at either end are the bedrooms, where they were kept at night. But there's a twist. Kept overnight in this bedroom, the birds were served an early breakfast. But kept overnight in this one, they got no breakfast and went hungry until mid-morning. The birds experienced this daily routine for almost a week.
So we give them 3 lots of experiences of waking up in the hungry room and 3 lots of experiences of waking up in the room that serves breakfast. But the important point is that the birds themselves didn't know which room they'd end up in on any given day.
But then Nikki changed the test. She allowed the birds to cache food in the evening before bedtime. She placed caching trays in both the hungry and breakfast rooms. The question was, where would they choose to store the food? Nikki wanted to know if the birds could use their past experience of the 2 different rooms and plan for the future, namely for breakfast time tomorrow. The results left no doubt.
What we found is that the birds cache about 5 times as much in the hungry room as they cache in the breakfast room. They can imagine what they're going to need the following morning when they wake up hungry, so they can solve a problem before it's even happened. So what this experiment shows is that the birds can plan for the future.
So the jays' caching behaviour is far more than mere instinct. They have a grasp of the past, but can also anticipate future need and, crucially, plan for it. This skill is very rare in the animal kingdom, and it's the 4th key ability needed to solve problems.
It's called mental time travel.
So that gives you an example then of how we study this ability to think about the future in these jays. We capitalise on their natural behaviour, their propensity to want to hide or cache food, and we ask whether, based on a single, unique, novel experience of caching food, having learnt where food is served for breakfast in the morning and when it's not, whether they can then spontaneously cache food in the room that doesn't serve breakfast in the morning. So the whole point is that it's a novel experience. They've neither been punished nor rewarded in the past for caching, so you can rule out any associative learning explanation because they've never had any opportunity to learn about whether caching is good or bad. All they've learnt about is where food is served for breakfast. But because it's spontaneous and because there's no obvious rule about when they'll end up in the breakfast room and the no breakfast room, the idea is that given the uncertainty of not knowing whether they'll end up in the breakfast room or the no breakfast room, they should spontaneously cache the food in the no breakfast room. And here you can see the design. So the idea is that during the morning, from 7 till 11, breakfast is served in one room, compartment A, but not in another room, compartment C. But throughout the rest of the day, they're allowed to eat food, but it's in powdered form in all 3 compartments. So all the rooms are associated with food other than at this small time window in the morning. And then in the absence of knowing which room they'll end up in the morning, they're given a novel test on the evening of the 6th day where they're given pine nuts and 2 caching trays. And given that they don't know whether they'll end up in the breakfast room or the no breakfast room, the prediction is that they should cache the food in the no breakfast room. And you see that by and large, that's exactly what they do. They cache far more food in the no breakfast room, the room in which they'll be hungry, than the breakfast room. There are other examples of the sophistication that these jays show in terms of future planning. And here's one example. Within a social setting. So what these birds do for a living is they don't only hide food, but they also steal the food that other birds have stolen. So they play both roles of cacher and protector of their own caches, and thief, pilferer of other birds' caches. So in this experiment, we had two conditions. They either cache whilst observed by another bird, or they cache in private. And then 3 hours later, they get the tray they'd cached in back, the observed tray or the in private tray, so the old tray, the one they cached in previously, and then they get a brand new tray. And the question is, other than recovering their caches, will they cache more? And if they do, that would mean taking food from the old tray and recaching it in a new tray. And the prediction was that if they are aware that other birds might steal their food, then in the observed condition, any food they don't want to eat, they should move to the new tray, because by definition, the observers don't know about the presence of the new tray, nor where in the new tray they might have moved the caches to. Whereas in private, it really doesn't matter. If you haven't eaten all the food you want, you could just leave it in the old tray because nobody knows about it anyway. And what we find is experienced thieves, so these have all been hand-raised birds, so we can know the precise experiences they've had. And these experienced thieves move the caches only if they'd been observed, and then move them to new places. If they'd cached in private, they don't move them. Only if they've been observed, only if their caches are potentially under threat. Now, the birds are never rewarded nor punished for moving the caches, so again, you can rule out an associative explanation. The idea here is that the birds are projecting their own past experience of being a thief to move them to new places. Now, of course, the skeptic might say, but how do you know it's anything about experience? Perhaps they just have a hardwired and innate propensity to do this. Well, that clearly isn't the case, because naive birds who have not had any experience of stealing those birds' caches do not do so. They just move very little food. So we argue that, in short, it takes a thief to know a thief, that this kind of ability doesn't only require an ability to plan for the future, it also requires an ability to think about what other birds might be doing. So this is an ability that relies not just on other times, past, present, and future, thinking about the future, what you might need to do to secure your future, but also thinking about what other birds might know. So other minds, and therefore the ability to secure not just a future, but your future, which was, of course, one of the central tenets of the mental time travel hypothesis, which was about projection of self, projection of time, and projection of self in time. So based on this work and many other experiments that we conducted, we argued for the convergent evolution of cognition in corvids and apes, that it required not just flexibility in terms of where they cache and when and who's watching, prospection because of future planning, but also other aspects such as imagination, for example, knowing how to solve a novel problem, and causal reasoning, knowing which of those possible solutions for the future might work in the absence of having any trial and error, any opportunity to learn associatively about what the right and the wrong action is. And we argued that actually in the corvids and apes, this is probably convergence because it's under similar selection pressures. Whereas in the coleoid mollusks, the cephalopods, the squid, the cuttlefish, the octopus, it's probably very different selection pressures. And therefore, in the case of their evolution, it's independent, not convergent. It's not coming together because of similar selection pressures. It's just completely different because of different ones. And the idea is that in the case of corvids and apes, there are strong social pressures. It's knowing when to cooperate and when to compete, as well as ecological pressures about time, when foods degrade or perish, and when foods ripen, but also knowledge about how to use and make a tool to get food that is otherwise out of beak or hand reach. Beak in the case of a corvid, hand in the case of a great ape. Whereas for the coleoid mollusks, the cephalopods, the social pressures are weak. They're not non-existent because, of course, there are social pressures in terms of sexual competition, but there are also ecological pressures in terms of predator-prey relationships. And in fact, it's probably the idea that the loss of a shell meant that essentially, as a coleoid mollusk, you're living lunch. There's high predation pressures, and the way they solve this is using dynamic camouflage. So this leads me on to the second part of my talk then, which is having looked at how good their cognitive abilities are in terms of their ability to remember the what, where, and when of past events, their ability to answer unexpected questions, their ability to remember the source of the memory, for example, in the cuttles, that whether they smelt it or saw it. And their ability to take prospective action for the future, eating fewer crab at lunchtime when I know that shrimp are on the menu for dinner. In the jays, the much more complex cognitive skills of planning not only for breakfast, but also for whether or not I'm likely to get my caches back, depending on who was watching when. Let's look on constraints on cognition, because magic offers a way to look at just that, to question these ideas about what blind spots in seeing might reveal and what roadblocks in thinking might suggest about such cognitive abilities in memory, in future planning, and in perception. And as I said at the beginning, magic is based on the idea that you have a subjective memory of what you thought you saw, which the magician can violate. And it's that violation of the expectation, the thing you are anticipating about the future, that leads to surprise. And because many magic effects are conducted visually, in fact, it's quite a useful tool in the field of comparative cognition to look at these kinds of questions about memory and mental time travel. So we argued that the jays, the scrub jay pictured here, for example, might be an unexpected audience, but that in a sense, a lot of the tactics that the jays go to when they protect their food from being stolen by others are tricks that magicians use. And how do I know? Well, aside from the fact that I have spent about 30 years studying the caching habits of jays, my dance partner, my tango partner, is a professional magician, and through him, I have vicariously learned a lot about magic effects, some of which we often perform as a double act. So here are some examples of things that jays do. They use shade to degrade information. Well, magicians do that too. They're very sensitive to the intensity of light and make sure that the lighting conditions are well set up before they perform their effects. Removing information by caching behind barriers. Well, magicians do that too. They often position themselves such that, for example, you can see this side of the hand and not that side of the hand. Degrading information by using distance. A magician will always say, don't come too close, stay there. And keeping track of who was watching and listening when. Well, that's not just the jays that do that. Magicians also pay keen attention to their audience and tailor their effects appropriately. So here's one example. So when the jays recache in private, one of the things I told you about when I was talking about the social side of future planning was that they just moved them to a new place if others had watched. And with a surveillance camera as pictured here, we can see exactly what the birds do. The food is moved and it's clearly visible in the beak. You can see the waxworms in the bill and you can see which cache site it's moved from and which new cache site it's placed in. But recaching in front of an audience is quite different. We call it sleight of beak because it really is like sleight of hand, except with a beak if you don't have hands. So you can see that the items are moved multiple times, and it's not actually possible to see whether the item was actually moved or whether it was a fake move. And like magicians, these jays also have secret pockets in the form of a pouch. So you can tell that Sweetie Pie, pictured here, probably has some worms in that pouch, but you've no idea whether they're worms or something boring. Maybe they're just bits of sand. And what the item she has concealed is, maybe it's worms or maybe it's boring old peanuts. So what I want to do now is to show you briefly a little video of some of the work we've done, where having said, well, these jays might be good candidates for looking at this because they seem to use tactics akin to those that magicians use in some of their effects. Let's look at what the jays understand about magic effects, and let's see if this can contribute further to our understanding of comparative cognition. Because, of course, if what we've thought about magic is correct, that it's based on you having a subjective experience of memory of what you saw happen, and then an expectation of what you think will happen that the magician should violate, then other animals that have mental time travel have this ability to remember this subjective what happened where and when, and have an ability to imagine what the future might hold, an expectation of what they think might happen. Then it should be possible for the magician to violate their expectations. But perhaps there's something missing in this equation, that it's just about memory and mental time travel when it comes to violation of expectations.
Magic tricks are a fascinating window on our minds.
Indeed. Do I have anything behind my ear? I doubt it. Anything in my hand? Of course not, which means that this should be physically impossible.
They highlight gaps in our perception and attention, which magicians exploit to disguise what's in front of our eyes.
I suppose the coin would be just there. Thank you.
But what about other animals? Do they fall for the same tricks we do? Could their susceptibility to magic tricks highlight flaws in their perception? Or could an ability to be misled actually reveal kinds of intelligence we didn't know they had? How did you become interested in doing magic tricks for animals?
Well, I've always wanted to be a bird. I've always wanted to fly and move around three-dimensionally and think like a bird. So that's how I got into science. But also through my passion for dance, I met Professor Clive Wilkins, who's artist in residence in the Department of Psychology, and he's a professional magician. And we both shared a great interest in memory and mental time travel through different perspectives, art and science.
I visited Cambridge University's Comparative Cognition Lab to see how the group are examining the mental abilities of jays using magic tricks.
Jays are extremely intelligent. We call them the feathered apes because they're on a cognitive par with the chimpanzees. And they're also very attentive. They really watch what you're doing. And so they became the perfect subject.
Elias Garcia Pellegrin spent months working with the birds in order to prepare for the experiments.
And one of the things that Eli was able to do was to train them to peck a thumb to ask them which hand they thought concealed the object he'd hidden.
This trick is known as a French drop. The jays don't fall for it, but perhaps that's not surprising. When humans watch the trick, we assume that the left hand is grasping the worm.
Your brain uses shortcuts when you perceive these movements. It just goes, well, what's the most likely thing to happen? Well, the most likely thing to happen is that when this hand grabs an object, the most likely thing is for a completed transfer to occur. And that's where magicians are very good, because they are very good at seeing how to make a movement which is perceptive so alike a real movement that the brain does not notice it. Even though there are particular kinematics that would tell you that this movement is fake, right? Like the tension. But you don't see that because you're just using the shortcuts in perception. However, birds don't need these expectations to survive because they do not have hands.
But the birds do fall for some other tricks.
Have a look. Where is it? Here. You're wrong. It's not.
On my visit, it wasn't just the birds being treated to a show.
Sam, do you remember the £10 note we talked about? Could I borrow it now?
Yes, I do.
Excellent. Thank you very much. Watch carefully.
When I watch this trick, I'm pleasantly surprised by the increase in my fortunes. But a similar trick was used to make the jays think their favourite snack had been replaced with a different one.
The £20.
Basically, what we did is that we showed Stuka the wax worm in this case. We pretended to deposit it inside the cup, and then we turned the cups around. Then Stuka went in and chose to retrieve the cup where she saw we put the wax worm in. But in doing so, she found that magically the wax worm had transformed into a mealworm. And then we measured how long it took Stuka here, or any of the birds that we tested, to actually ingest, to eat the worm, okay? And we found that when we did this case, at the value condition, so their first preferred item magically transformed into their less preferred item, they took way longer than when we did an up value condition. So their less preferred item in this case transformed into their most preferred item. Think about the magic effect that Clive did for you. Okay, you were happy because a £10 note became a £20 note. That's great, right? But what if Clive takes your £10 note and transforms it into £5 note? It's not that happy anymore, right? You're not that willing to take that £5 note anymore. You want to give it back. You want Clive to transform it into a £10 note again, don't you? That's what happened here.
Are you doing any magic experiments with any other animals besides squirrels?
We're hoping to do some magic effects with primates, and we're also excited about exploring some of these ideas with cephalopods, cuttlefish, octopus, squid.
You do get attached to these animals, especially when you spend a long time working with them. You notice their different personalities. Gone are the days of like scientists with white lab coats not having any feelings for their subjects. We've learned too much about what's going on in their minds to just treat them as just banal subjects. Because these are not banal subjects. These animals can think, they can feel, they understand the past, the present, and the future. And I don't see any point for me not to treat them as such, if this makes sense.
So that gives you a feel then for the way in which we've used magic effects to test these abilities.
Magic.
And these are the effects we do. So palm transfer requires this kind of action, which requires the use of a thumb. French drop definitely requires a pincing action of the thumb. And fast pass is one that much more functions with movements that work like a wing. And so this is just showing some of the research. This is my PhD student, Elias Garcia Pellegrin. And as you can see, the jays are very tame and they're being asked to observe what Eli's doing with his hands. And the test is then they should peck the thumb of the hand in which they think the worm is in. And then here you see the palming technique. And you see the jay's not fooled. Here you see the French drop. And you see the jay's not fooled. Here you see the fast pass. And you see the J is fooled. So the action where the hand moves like a wing, the birds are fooled by. The idea is they have an expectation of how hands move when hands move like wings, because that's a shared biomechanical ability. That's a movement they can make themselves. Even though these birds have been hand raised and had lots of experience of me and Eli and others in the group doing this thumb and finger movement to feed them worms, it's not a movement they can make themselves. And here you see the results. So they're very good at the palm transfer and the French drop, ones that require opposable thumbs. In other words, they're not fooled by them. But the fast pass that doesn't require an opposable thumb and finger action, they are fooled by. The one that works like a wing, they are fooled by. That is something they can develop an expectation of based on what they thought they saw, because they can make that movement themselves. This is just to show that the people had the same view as the Jays. So you're going to see the J bit first and then the bit for the human, just using the French drop. And you see that the humans, their percentage correct was low. They were fooled by all three effects. So in order to test this hypothesis that it's about shared biomechanical ability, we then turn to primates, non-human primates, all of whom have hands, but some have opposable thumbs and some do not. So capuchins and squirrel monkeys have opposable thumbs, but the marmosets don't. So the prediction is the marmosets should behave like the jays, and the other monkeys should behave like humans. And here's a little video to show the experiment in action. So here you see the results. So the precision grip, when they use the opposable thumb, sure enough, the marmosets are not fooled. They behave like the jays, whereas the squirrel monkeys and the capuchins are fooled. They behave like people. But when you reenact the effect using the power grip that only use fingers as opposed to a finger and an opposable thumb, the marmosets, like the other monkeys, are also fooled. So that supports this idea of embodied cognition, that it is about this shared biomechanical ability. It's not just observing the shared biomechanical ability or having experience of that ability. The Jays being hand raised had watched me and Eli and many other people in my lab hold the worms using our opposable thumbs and fingers, but they can't make the movements themselves. That's what seems to be critical. And that's what seems to be critical of this embodied cognition, and also why some aspects of dance, such as ballet, are so difficult, because you have to interpret the movement based on your own body. So if a dance teacher who's a male and he's large illustrates a movement that I need to reenact myself, I can't literally just imitate it. I have to adapt it to my body because I'm not tall and I'm not male. And so I have to take account of the different shapes of our limbs and our movements in order to reenact the movement. So I've argued the case for how embodiment shapes not only your ability to manipulate an object, my ability to hold this little espresso cup of coffee, holding my thumb and my finger or in the palm of my hand. But these movements, this ability to make these movements, also affects the way I interpret the world, the way I interpret what I thought I saw and what I thought I remembered. So I've shared with you some of this work based on the idea of having hands with fingers and possibly an opposable thumb or not, depending on whether you're a marmoset or a capuchin monkey. The ability of fingers to work in a similar way as feathers in the case of the wing of a bird such as a jay, or not in the case of an opposable thumb, or the power grip when fingers do that, because feathers don't do that. And what I'm interested in doing next is looking at these coleoid mollusks, these cephalopods, all of which have 8 arms, and some of which have tentacles too. So the cuttles, for example, have 8 arms and 2 tentacles. The octopus, despite what it might say on the dinner menu when it served you octopus tentacles, have 8 arms but no tentacles. But how does that shape the way you might build these expectations about what you think you see and what you remember? And how might this impact upon cognition? Well, we haven't really started the work yet. We've done a lot, obviously, on cephalopod cognition, for example, their ability to remember what happened where and when, and their ability to make prospective decisions about eating less crab at lunchtime if there are shrimp, their favourite food, on the menu for dinner. But in a sense, what we want to look at is their naturalistic behaviours to inform cognition. And therefore, I've got very interested in dynamic camouflage, because that's what these cephalopods, these coleoid mollusks, do for a living. And here's one example. This is using inking to disguise themselves, to hide the transience, as magicians would call it. So there you see them disappear and reappear, which is exactly something that magicians do. They call it hiding the transient. And here's another example where they're even able to use this dynamic camouflage to match movement. So these are giant cuttlefish that mimic the movement of the algae. So if I can get this to play. There you can really see the giant cuttlefish versus the algae. But look how in tune they are, the synchronicity of their movements. So in a sense, I'm thinking of dynamic camouflage as a kind of caching, but rather than caching food and preferred objects, they're caching themselves. And the questions we want to know are whether they use tricks akin to those that magicians do in these abilities to hide themselves, to do this dynamic camouflage and signalling. So there's a famous example from Charles Dickens, not Charles Darwin, but Charles Dickens' time, the pepper ghost illusion. And that relies on illumination and refraction and perception. So in this particular example, there's the illumination of the apparent ghost. There's the reflection and refractions due to the mirror, the refraction, the angle of the mirror, and then the perspective of what the audience can and cannot see from where the audience is sat. And we're interested in seeing whether there are elements of this that might be akin to the kinds of things that the cephalopods do in their use of dynamic camouflage. For example, illumination, the whole idea that they make the illumination themselves, they light themselves up through their bioluminescence. And the reflection and refraction, told you already about the giant cuttlefish pretending to be moving seaweed. There's another lovely example by Roger Hanlon and Messenger about the fact that the octopus will pretend to be a rock and then just move. The rock will move in line with the water and the refraction of sun, the refraction and reflection of the sun on the water, that leads you to not even notice that the rock is moving. And then there's the whole idea of, do they use perspective as well as refraction, refraction, and illumination? Do they, just like in the Pepper's ghost illusion, use perspective as well to misdirect and optimize camouflage? For example, by knowing when to conceal themselves and when not to, and the various tricks they might use to optimize and misdirect the information of the audience. And so with that, I will finish and just thank all my collaborators, both my feathered friends and all the people in my lab and all the funding bodies, and to all of you for listening. And I've deliberately tried to finish a little bit early to give you 15 minutes or so if you would like to ask me any questions. Thank you very much.